All right, hi everybody. It is my pleasure to introduce today's speaker, Mark Hoy. I don't really know how to pronounce your name. I'm really sorry. I hope that was okay. So Mark received his PhD in cognitive science from Brown University, where he worked together with Joseph Austerwal and Viri Gushman on teaching and social learning. And after that, he went on to do a postdoc at UC Berkeley with Thomas Griffiths, where he was affiliated with the Learn and Verify group at the Department of Electrical Engineering and Computer Sciences. And since last year, he's a faculty fellow at the Center for Data Sciences at NYU. And in the fall, he's going to start his own lab and will also be looking for PhD students and postdocs. So if you think his work is really cool, which you're probably going to think, then, keep that in mind. His research combines different techniques and provides insight into human planning and social cognition by developing computational theories, for example, using probabilistic models, reinforcement learning, neural networks, and then testing those theories experimentally on humans. So Mark, if you want to start, that'd be great.
Great. Yeah, thanks so much. Can everyone hear me?
Yes.
Great. Awesome. I'm excited to talk to you all about some work that my colleagues and I have been doing, thinking about human planning. So I want to start by kind of pointing out something maybe that's obvious, but when we look at human cognition, something that really stands out about it is how general and how flexible it is. And when I say that, I mean this kind of in contrast to, say, other species that can do pretty sophisticated things. So, for example, like otters can use tools, lions can cooperate to hunt to kind of achieve shared objectives. But other species tend to be very specialized in what they can do. So, you can't get an otter to cooperatively hunt, and you can't get lions to use tools. And when we look at most AI systems that exist today as well, there's a similar kind of specialist kind of nature to them. So like, things like AlphaGo, maybe they beat humans at chess and Go and so on. And maybe Google Translate can translate between more languages than any human can, but you can't get AlphaGo to translate, and you can't get Google Translate to play Go. And of course, recently in the last like 6 months, we've seen a lot of discussion around like large language models and whether those are kind of more general intelligences. But for the most part, most AI systems that can accomplish tasks, they're very specialized as well. But when we look at people, what's kind of remarkable is that a single human being can learn to do all of these tasks. Obviously, this is just a very small slice of all the things that any one of us could probably do or learn to do. So when thinking about kind of what makes human cognition so general, one of the kind of key pieces of the puzzle, one of the key kind of cognitive mechanisms is this capacity we have to plan. And when I say plan, I mean kind of the ability to kind of form a mental representation of the world and reason through that representation and kind of use the results of that reasoning to kind of guide action in a dynamic way, or even just in general. And so, yeah, unsurprisingly, then planning is something that psychologists have cared about for a very long time. Psychologists and AI people and so on. Going back to work by Tolman, thinking about how we form cognitive maps, how organisms form cognitive maps and use those maps, to kind of work in the 60s by George Miller and colleagues, thinking about this idea of like a plan as a kind of representation that an organism has of its own behavior in the future that it uses to guide its behavior. And then famously in the late 60s and early 70s, Alan Newell and Herbert Simon kind of developed a computational account of what it means to engage in planning and problem solving and kind of solving complex problems in a flexible way. And so the Newell and Simon kind of story can really be summarized in the following way. You kind of assume that as like a decision maker, you have some kind of representation of a problem. For example, in chess, you have a representation of board, pieces on the board, how those pieces interact, and the goal of winning the game, checkmating your opponent's king. And oh, what happened? Okay. And yeah, given this representation of a problem, you can do computations over that representation. So for example, if you have a representation of chess, you can kind of generate a tree and do tree search over possible states of that over possible states of the game, and use that to guide your actions. And this idea of kind of doing heuristic tree search, we can kind of think of this as an example of what I'm going to call kind of the standard model of planning, where we kind of have a representation, and we kind of use that representation to generate possible actions, and then we do computations using the representation and those possible actions. And this idea of kind of separating the representation and the computation over actions, this is, it's kind of at the heart of classical planning, but also at the heart of, a lot of ways we think about sequential decision making in general. For example, reinforcement learning, where you kind of typically specify a problem as like a Markov decision process, and then reinforcement learning algorithms kind of operate over that representation to learn policy, a good optimal policy. But what's kind of funny about this this formulation of kind of having the representation and then you search for actions over that representation is that this representation is typically conceived of as like a fixed thing. And we've known for a long time, psychologists have known for a very long time that we don't operate with like a fixed representation of problems. And evidence from like insight problem solving, analogical reasoning, and studies of expertise have kind of revealed this for a very long time. And this isn't something that Newell and Simon were totally oblivious of in their kind of big book on human problem solving. They cite a really cool work where they kind of studied experts looking at a board and kind of track their eye movements. And that's what I'm showing you here on the right here. And what you can kind of see from these data is that really people are not kind of processing the full board, but rather they're selecting out kind of subset of the objects and presumably thinking about a subset of the interactions between those objects when they're solving the problem, particularly when an expert is solving the problem. And so, there's this kind of old question of, on the one hand, we have this like we have like kind of the full richness of a problem of the world, and then we have this kind of simplified version of the world that is useful for problem solving. And there's this kind of old question of, okay, how do humans go about representing tasks in a way that allow them to plan? And so this is kind of the starting point for some of the work that we've been doing, kind of thinking about, okay, how does this work? What are the kind of underlying principles here? And the proposal that we developed is this idea that people are engaged in a process of what we're calling value-guided construal, and they construct these kind of representations that we call value-guided construals. Okay, so that's kind of the kind of general approach here, kind of motivation for a lot of this. To actually study how people form representations of problems and use those to plan, we developed this task, this maze navigation task, where participants were shown this kind of 2D board like this, kind of getting a bird's eye view of a maze, and they could control the little blue dot down there in the lower right-hand corner, and their goal was to get to the goal state marked in yellow in the upper left, in this case. And on each trial, there would be this black cross in the middle that you couldn't go through, and then also these blue Tetris pieces that would move around on each trial. And you can't go through those either. And so a trial looks something like this, where you start with the black cross, and then when the participant's ready, they indicate it, and all the goal, the agent, and the obstacles appear, and then they navigate to the goal, and then afterwards we ask them to get a measure of the kind of representations they were forming when solving this task. We ask them, okay, for each of these blue obstacles, how aware of each obstacle were you at any point when solving the problem, when navigating, or when planning and navigating? And the first thing about this this experiment is that people, maybe unsurprisingly, they can look at the maze, they think about it for a couple seconds, and then they can execute a plan, even though they've never seen this maze before, this particular maze before. But maybe more importantly, the measurements we're getting at the end of each trial allow us to kind of look at, okay, for each obstacle, how much are they paying attention to it, and kind of map out collectively for each of those obstacles, kind of the full map of awareness. In this case, it's reported awareness, but we use other measurements as well. And so this kind of data is what we're trying to explain. We're trying to explain how is it, like, what explains this pattern of attention, of awareness to each of these obstacles. Okay, and so yeah, so the kind of approach we take is computational modeling, and as I said before, we can kind of start with this standard model of planning. Heuristic tree search being an example of it, and we can kind of think of it at a very abstract level as involving first, there's a task out there in the world, and then you engage in a process of planning over that task, over that representation of the task, and then you take actions based on the plan that you compute. And in these maze scenarios, this looks something like this, where there's a kind of fully detailed maze over here on the left. Then you engage in some kind of planning over that maze. Here I'm showing you the result of running like an A-star search algorithm over the maze, where the kind of darker green dots indicate the plan that it ends up finding. And then you execute that plan in the real world. So the first two here are kind of what's happening in your head. The kind of basic idea that we're proposing is this idea of value guide construal, which there's still a task out there, and you're still doing planning, and you're still taking actions, but between the task, the kind of raw task, and the planning process, and it may be in parallel with the planning process, what's typically called the planning process, we're proposing there's this kind of process of task construal, which is you are kind of forming a representation of the task that you are also using for planning. And this kind of construal process and kind of action planning process are kind of working in tandem to produce goal-directed action. And so again, in this maze setup, it looks something like this, where you have the task, like on the left here, and then you are engaged in a process of task construal, where you're kind of selecting out certain details of the problem, and then you're planning over that kind of simplified representation of the problem, and then you get a plan, and then you execute that plan. And one thing I want to point out here is kind of a methodological thing or approach, is that the way we're going to approach this is kind of think about the planning process as almost like a black box. This planning here, this kind of plan pi c thing here, it's kind of a black box function where we kind of assume that, okay, well, we're going to choose some task construal and feed it to this planning function, and then we're going to get out an optimal plan for that construal. And the reason that is because there are many ways in which you could plan over a given representation of a problem. And we're trying to kind of focus in on this idea of, okay, well, if we're going to get at the task construal process, how can we kind of bracket for now the question of kind of the kind of specifics of the planning algorithm on the left here. But of course, that's like a very important, interesting question that I'll come back to later. Great. So yeah, so to kind of walk through in more detail, like how we're thinking about this, the idea is basically that we can think of this process of forming a representation of a problem for doing planning or during planning as a kind of decision-making process in and of itself, kind of meta decision-making process, where you're choosing a representation, and each choice of a representation, each potential, has a utility or a value associated with it. And that value function is computed based on this equation here, which is for a given construal C, what is the utility of the plan that you get from choosing that construal minus some notion of cost of that construal, big C. And so this first piece here is, what is the space of construals that we're even considering, that we're doing this choice over? And the way we're thinking about it here is maybe the simplest way you could possibly do this, which is to say, okay, well, you have, the task stimulus here on the left, and we assume that there's some kind of perceptual process that happens where you're able to parse the problem, this stimulus, into some set of local interactions, some set of local objects. So for example, you have this cross in the middle is one object. It's the most consistent object across all of the trials. And then on a particular trial, you have, a Tetris block here, and then you have each of the Tetris blocks in the maze. And so we're assuming that, when you look at this, you're kind of getting these set of primitives, basically, that you work with. And so given those set of primitives, then we can say, okay, well, what is the subset of those that we're going to think about? And, for example, we could choose the black cross in the middle, and then this subset of the blue Tetris pieces. And then given those, we can kind of bind those into what we're calling a construal, which is this kind of model that leaves out certain details of the problem. And that's what we have here on the right. And the kind of key thing is that so far I actually haven't talked about planning with this yet. This is just kind of selecting out a bunch of, objects in the environment, in the stimulus, and kind of binding them into a representation of kind of the global environment that is leaving out certain details. But we can take this construal and ask, well, what if we actually took this and planned with it? What plan would we get? And that's what this pi c here is denoting. And so, for example, if you took this construal on the left and planned with it, basically you're assuming that the blocks in gray are not present and the blocks in blue and black are present. If you plan with that, you might get a plan like this in the middle. And within this kind of imaginary world of the construal, this is a great plan. But if you actually executed this plan in the real world, you would end up crashing into one of the blocks because in reality, there is a block there and you can't go that way. And so the behavioral utility of this construal kind of through this planning process is low because if you were to use this construal to plan and then execute that plan, you wouldn't do very well on the task. And so, but we can ask, okay, well, what about other construals? What about other choices of representing the task? Well, okay, what if we include this block over here? So now we include this block, we do planning over that version of the task. And now that plan, when it's executed in the real environment, it would do well. So this construal, in contrast to the other one, has a good utility. Okay, so that's kind of the utility portion of this equation. Now, what about the cost? Well, so there's a lot of ways to conceptualize cost. You can think about like a budget or kind of time to plan or something like that. The approach we took was kind of the simplest thing that kind of gets at this idea of representational cost, which is to say, what is the complexity of this construal on the left here, kind of before you even do planning, kind of separately from planning entirely. And the way we do that in this very simple setup is to say, okay, well, what is the number of obstacles? What is the number of objects you're paying attention to? And so from that perspective, the construal here on the left is not great because there are kind of extraneous details that you're including in this representation, even though it gives you a good. And so in particular, we could remove these two obstacles and get this construal and compute a plan on that version of the maze. And when we execute that plan also does well. So it has good utility, and it doesn't include those kind of extraneous details. And so actually, this particular construal is the optimal construal according to this loss function that we've defined. And so what the model allows us to do is, for a given maze, we can derive what the optimal construal is, or a kind of near optimal distribution over construals. So yeah, so before I kind of return to the data, I kind of want to just kind of talk a little bit about kind of how I see these ideas kind of fitting into kind of the larger literature and various literatures, and in psychology, neuroscience, and AI. And the kind of first thing that we were excited about with this is that this kind of old idea in cognitive psychology of ad hoc representation. So as you kind of go through the world, you form representations of the world that are kind of temporary. So the kind of classic example is like if you're going to throw a party, maybe you come up with this category of things I need to buy to throw this party. And that's not like a natural kind, but it's a useful category of things in the world to think about. And so we can kind of think about construals as a kind of ad hoc causal representation that's used for planning. The other thing is that we can really think about this construal process as a kind of variant or a form of kind of top-down cognitive control, in the sense of you're kind of selecting out certain kind of affordances in the environment, and that is kind of being fed into another cognitive process, namely planning. And so it's kind of like a metacognitive process in that sense. The third thing is that we're kind of approaching this. I kind of mentioned before that we're kind of abstracting away from the details of the particular planning process, and this is kind of in the spirit of kind of a computational level or resource rational theory of what it means to form representations of a problem when you're engaged in goal-directed planning. And finally, kind of related to this point about cognitive control, is this idea that we can think of the construal process as really a meta-optimization process, in the sense that planning, given a model of a problem, planning is an optimization process, right? So like I give you a problem to plan over, you do heuristic research over that problem, for example, and that process is an optimization process. You're trying to find the best plan within the parameters of that problem. And then the construal process is kind of meta-optimizing that optimizing process. You're kind of feeding in different representations of the problem to this optimization function, and you're getting out solutions. And so there's this process of kind of coordinating computation between this like higher level of task construal selection and lower level of planning, kind of action optimization. So a way to think about it is like model optimization and action or policy optimization. Cool. So yeah, so we can kind of coming back to the question of kind of the experiments, we can ask, okay, well, we have this kind of account of what it means to form an optimal construal. And that we can ask the empirical question, do people form optimal construals in these types of tasks? And so, like I said, this gives you a prediction. The model gives you predictions for a given maze. And so this is the maze that I showed you that I kind of walked through before. And if we, yeah, so we can look at this maze and we can compare it to the responses from the experiment that I mentioned before. And that looks like this in this case. And as you can see, there's kind of a nice qualitative alignment between what's going on in the model, what the model predicts would be the objects you pay attention to, and what people are reporting as having paid attention to each of the objects. In particular, you kind of have the, people are paying attention to kind of these two, this kind of set of objects, and largely reporting not paying attention to this set of objects on the left. And this is another example where people report paying attention to the ones on the left and ignoring the ones on the right. And then there's a third example where, again, on the top, the model predicts you would pay attention to these three obstacles, and those are the three that people report paying the most attention to. So this is just to give you a sense of kind of qualitatively how these things line up. Yeah, as a kind of first kind of very coarse-grained quantitative analysis, we can ask, well, okay, the model currently, it kind of makes these binary predictions about what's going to be ignored. And so we can ask, okay, for the ones that are predicted to be ignored, what do people tend to report as attending to in those cases? And in that case, people consistent with the model tend to report ignoring those obstacles, and conversely, for the obstacles that are predicted to be attended to, people tend to report paying more attention to them. Great. So yeah, so that's kind of like abstractly what the model is doing and kind of picking up on. I want to now kind of walk through another example, or kind of intuitive example, that I think really kind of pulls out what this account is picking up on that's distinct from a lot of other kind of ways of thinking about planning and kind of the standard planning model. So in New Orleans, there's this very long bridge that goes across the lake next to New Orleans. And it's, you know, if you're in New Orleans, for example, and you're trying to get to the other side of the lake, then on a normal day, you would obviously take this bridge because it's the shortest path. That's why they built the bridge. But now I want you to imagine that there's a truck on the bridge, and you're watching the news and you see that there's a truck on the bridge and it's blocking all the traffic. So now you can't take the bridge to get to your destination from the south side of the lake. And you have to take this longer route that goes around on this side. And what's interesting about this, this situation is that even though you never get close to this truck, you're always going to be far away from this truck along the path you take. The truck is like a really important detail of the world that you have in your model of the world when you're solving this problem. And so what this illustrates is that you might have thought that, you know, the sequence of that, like kind of proximity to the sequence of that, to the path you took might be predictive of, you know, what you report paying attention to or attend to. And there is, you know, we do find evidence of that, but what this is showing is that that's not necessarily the case, that there are things in the world where they can be really far away from the path you end up taking, but they're highly relevant to the choices you make, and so that you are going to include them in your representation of the problem. And so we designed a kind of new set of mazes that embody this kind of intuition, where, again, you're trying to get from this start state to this goal state, and you have the obstacles, but there's kind of qualitatively different, each obstacle kind of like plays a different role. So here, these obstacles are, you know, relevant obstacles. They affect your decision making, but they are near the path. And then you have this obstacle down here that's a lot like truck that is far away from the optimal path, but it's really critical for understanding, for kind of your choice to have taken that path. Because if this obstacle wasn't there, you could have just gone to the right and gone up. And then you have these irrelevant obstacles, which in the full context of all these other obstacles, don't really make a difference for the choices you make. And so what value-guided construal is going to pick up on through the kind of process that I described before is that the relevant obstacles are going to be picked out, because when you plan with those combinations of relevant objects, you get a good plan, and all of them are needed to get that good plan. And so, so the model would predict that you pay attention to this, this, and this. And so, yeah, so we ran, you know, the original version with the kind of self-reported awareness, but then we also ran a version where we asked people for their accuracy and confidence on these recall probes, where we removed all of the obstacles after they navigated. And then for each obstacle, we came up with a kind of pseudo obstacle that hadn't appeared anywhere in the task. And we kind of placed the original obstacle and that pseudo obstacle, that kind of distractor obstacle, and asked them, okay, which one was actually in the problem that you solved? And so this gives us another a slightly different measure that kind of is accessing memory more directly rather than self-report. Okay, so again, we have the relevant obstacles and irrelevant obstacles, and then we have near and far obstacles. What I'm showing you here on the right is the kind of accuracy and confidence scores from those memory probes, where the red X's are these irrelevant obstacles. This is just one example of one of the mazes. And green is relevant, and then in particular, the green pluses are these relevant but far obstacles, far from the optimal path. And what you can see is that as predicted by the model basically predicts this red-green kind of separation, and we see that. Okay, so we can also ask whether, is this construal process, or are the responses that we're getting, are they not the result of this kind of active selection process, but the result of some kind of, are they a side effect of other processes that have already been kind of studied a lot in the literature? Other kind of classic standard planning processes or decision-making processes, or even perceptual processes. And so, our model is kind of saying you have task, you have planning, and this, you're kind of doing task construal in tandem with planning, and it's kind of an active process. But you could imagine, maybe people are just planning in the normal way, in the way that kind of standard accounts would think of it, but there's like other processes going on the side that cause you to give responses in a certain way. And so we wanted to test this. We wanted to kind of rule out a number of alternative processes that are unrelated to this kind of active construing process. And yeah, again, so this is another example from the previous experiment. What our model predicts, what value-guided construal predicts, is that you would pay attention to these obstacles in blue and ignore the obstacles in gray. And we were interested in kind of comparing the predictions of that model with models based on heuristic search. And so there are a lot of versions of heuristic search, heuristic tree search out there, but they can kind of broadly be kind of grouped into one of two families of heuristic search algorithms. So one is closest to like heuristic tree search, which can kind of be thought of as, or referred to as, like a trajectory-based heuristic search algorithm, where you're kind of you're simulating trajectories in a given model, and you're using those to compute the best sequence of actions to take. And so I'm going to show you an example of one of these algorithms called real-time dynamic programming. And in this version, it's also given a heuristic, so it kind of knows it's using the Euclidean distance or Manhattan distance to the goal to guide its search process. And this is a kind of four rooms domain, a much simpler domain than the ones we used. But basically what these types of algorithms do is, from the start state, they kind of roll out candidate sequences of actions guided by the heuristic. And as they kind of explore the space, they can kind of construct, working backwards from the goal, a sequence of actions. So what I'm showing you in green here, those are the states where it said, oh, okay, I know how to get to the goal from here. And so it does that. It kind of rolls out a bunch of times until it's able to converge on a plan from the start state to the goal state. So yeah, so on our tasks, it would look something like this, where you're rolling out from the start state, and if you notice, it kind of spent a lot of time over here in this dead end, but eventually it kind of got out and is able to figure out how to get to the goal and can construct a sequence of actions, can plan a sequence of actions to get to the goal. And the reason why it ends up exploring this dead end a lot is because of the nature of the heuristic. So the heuristic says, oh, move towards the goal, this kind of general direction of the goal. And it needs to basically kind of unlearn the associations here of going towards the goal in order to explore sufficiently that way. So that's one algorithm. And what we can do is say, okay, well, if people are engaged in this process, then, and they're doing this process over the fixed grid, over the fixed maze, what would we expect this algorithm to pay attention to, just as a side effect of running this algorithm on this representation, on this fixed, fully specified representation? And so what we looked at was the log hit count of that kind of those rollouts. And so what I'm showing you here are those log hit counts. And the reason why we used the log was because, as you saw, it kind of spent a ton of time over here. So there's a very long tail of kind of hit counts. But yeah, you end up getting this pattern of results where if people are executing this kind of algorithm on, again, the fixed representation, so we're kind of assuming there's no construal happening, we're just assuming the fixed representation, this is what you would expect this algorithm to report paying attention to. Okay, so maybe you're thinking, well, okay, that's one type of heuristic search algorithm, not a very smart kind of heuristic search algorithm. People are smarter than that. Well, there's another family of algorithms called, that we refer to as graph-based heuristic search algorithms. And things like A* are a good example of this, where you kind of, rather than kind of just repeatedly generating trajectories from some start state, you're actually constructing a graph from the start state. Again, you're kind of rolling out, but you're at the same time constructing the graph. So you're kind of doing a little smarter thing. And then you're doing planning over that graph. And so it looks something like this, where you're kind of, you're building out a graph representation of the problem. Again, this is in the fully specified representation of the problem. So you're building out this graph and you're doing planning over it, and you can eventually find the sequence of actions that gets you to the goal. And so you're not doing this kind of rolling out, like spending a lot of time down this dead end type of thing. But of course, you have to explore, you have to realize, you have to go down this dead end to realize that it is dead end. And again, this also, like the trajectory-based one, it has the heuristic that says that, so it knows about the Manhattan distance between its current location and the goal. So it's kind of, again, it's heuristic guided. And yeah, so we can, oops. So we can, again, ask, well, if we ran this algorithm, what does it bump into? What is it, and what would we expect as a byproduct of that bumping into to have it, that it would report paying attention to? And in this case, we can just use the kind of raw hit counts, and here, that graph, it results in kind of hitting these things this number of times. Okay, so those are two heuristic search algorithms, two planning algorithms. We also looked at a couple of other measures, things related to kind of the distance to bottleneck states, the SR, things related to a version of the SR, and then some kind of perceptual, kind of landmark-based things like what is the minimum distance to the path, what is the distance to the goal, start state, the closest wall, the center of the maze, and so on. And the kind of key, again, the kind of thing I want to emphasize here is that we're trying to contrast the idea of kind of adapting the maze representation versus processes that operate over a fixed maze representation. And of course, we could do both, but we're just trying to isolate the effect of adapting the maze representation, even when we account for a whole bunch of ways in which processes could operate over a fixed maze representation. So to analyze this, again, for each of these models, we get a prediction, we get a score for each obstacle. And what we did was we fit a single model that included each of these as regressors, each of these the predictions derived from these as regressors. And we fit this model to recall responses, the memory response that I mentioned before. And then to understand kind of the importance of each of those in the context of all the others, we removed each one, and then we refit the model, and we compared the lesion model to the original model. What I'm going to show you here are these kind of the effect of each of these lesions. And so a bigger change in fit indicates that predictor was more important for explaining the data, even in the context of all the other predictors. And so when we look at value-guided construal, this has a relatively high kind of change in fit. But then when we look at all these other regressors and look at the effect of removing them, we see that they don't have as high fit, although in some cases they are kind of predictive. Great. So yeah, so that kind of gives us a sense of like, okay, this construal process is really picking up on something that is distinct from many other processes operating over fixed representations. Great. So something that comes up a lot when discussing this, I kind of mentioned before that we were thinking about this as a kind of resource rational process, or kind of taking a resource rational lens perspective on this question. But we can what's kind of nice about that is that, kind of once we've established kind of normative theory, we can start thinking about, okay, what are plausible algorithms for actually optimizing this type of thing? In the paper, we explored this a little bit, but I think a lot more work could be done, and it's interesting. And so I'm just going to kind of walk through a very rough sketch of how this might work, just to kind of give some intuition. And yeah, so the kind of way so earlier I mentioned that we can kind of think of this task control process, a kind of meta optimization process. And we can kind of, again, reframe that as a kind of search process over some space of construals. And the way you could think about this is, well, for a given maze and for a given kind of partitioning of the objects, there is a space of construals that correspond to all subsets of those objects. So, at one extreme, you have the totally empty construal, and at the other extreme, you have the full construal, kind of all the details. And then in between, you have this kind of lattice of different kind of subsets of those construals, of those objects. A way to kind of think about this is that, we are somewhere inside of this big set, this big lattice is the optimal construal. And so then this just becomes a search problem, but again, over the space of construals rather than over the space of actions. And, there are many ways to solve this search problem. We can start, for example, we can just start with, breadth first search evaluation. We start with the empty construal, then we kind of add each object in, evaluate it. And if that doesn't work, then we go on, we look at pairs of objects, and then eventually you might get to the optimal construal. And so there's a lot of ways in which, we can search through this space. This is just one way. You could use heuristics to search through the space. You could be guide through this space in a more intelligent way. But this kind of just gives us a sense of, okay, well, once we think about this as a kind of optimization problem at the level of representation, then we can start throwing all sorts of possible algorithms at that problem. Great. So I'm going to now talk a little bit about some more recent work that we've been doing, kind of thinking about how this idea of construal can really be used to explain other phenomena that have been identified in the problem-solving literature and kind of sequential decision-making literature. And one very interesting set of results, kind of classic results, is this idea of functional fixedness. And so the kind of classic functional fixedness experiment is the one by Dunker from the 40s, where is Dunker's candle task, as it's often called, where you bring people into the lab and you give them a bunch of objects that look like this, where you have a candle, you have a book of matches, and you have a box of tags. And you tell the participants you need to mount the candle on the wall and light it. Where mount, kind of think of it kind of broadly scope. You don't have to, it has to be at a high level on the wall somehow. And so if you give people this problem, they try various things, but they aren't able to solve it. So for example, they'll try to like melt the candle to the wall, they'll try to tack the candle to the wall, but that won't work because the candle will crumble. And so, yeah, maybe just, if you haven't seen this before, take a second, think about what you would do. So, yeah, so the correct answer here is to actually empty out the box of tacks, tack the box to the wall, and then put the candle in and then light the candle. And this is funny because once you see this, it's like totally obvious, like, oh, I should have thought of that before. But people have trouble figuring this out. And this is often described as, the process of using the wrong task representation to solve a problem. And in particular, you're kind of construing the box as a container and not as a support for the candle. And so you kind of get functionally fixed on the box as a container, and that blocks you from using it as a support. And so we're interested in whether this kind of idea of value-guided construal could be used to study these types of phenomena. And so to study this, we developed another version of our task kind of inspired by this idea that, as we're kind of moving through the world, we kind of see different objects at different levels of abstraction. So for example, if you, are traveling in an airport, you can think about the various terminals in the airport as kind of just these big objects out there in the world. Say if you're kind of trying to get from one to the other in a shuttle bus. Or you can think about a particular one in much more detail. So if your flight is going out of a particular gate, you'll think about that particular gate. Is there food nearby? Where's the bathroom, and so on. And so we designed a version of these mazes that kind of picks up on this idea, where at kind of one level of abstraction, there are blocks in the task. So again, you're starting from this blue circle and you're trying to get to a goal state, and the black walls here are on every trial. And from trial to trial, there are these blocks, and these blocks are constructed as follows. So there are these 3x3 blocks that are kind of bigger, and they're this color, this kind of greenish color. And then there's a kind of microstructure to each of these blocks, notches. They each have a notch in them, which is kind of coded as a slightly lighter color. And the blocks block you except for where the notches are. So you can go through the notches to get to the goal. And this kind of induces two kind of sets of construal. So if this is the maze on the left, one kind of possible way to construe the maze is only in terms of blocks. So don't even think of the notches. And on this particular maze, that's fine. You can solve this maze without kind of thinking about any of the notches. If you just think about these blocks, you just know that you can't go up this way to get to the goal, and you don't want to bump into this block, and so you can go this way to get to the goal. So the blocks only construal is sufficient here. But now if we move this block up here, the blocks only construal is no longer sufficient for solving this problem. Now you actually have to start thinking about, okay, well, how do I get through one of these blocks to get to the goal? And in this case, this notch over here is kind of the key thing that you have to go through to get to the goal. You don't have to pay attention to all the notches, but you have to pay attention to at least one notch. And so we designed an experiment where we basically put people into one of two conditions, one of two training conditions, where they were trained on a sequence of mazes where to solve them, going through a notch was unnecessary. And so you could solve them by just construing it in terms of blocks. And then we came up with another set where it was necessary to go through one of the notches to get to the goal. And so we have the notches unnecessary and notches necessary conditions. And then we had a set of test mazes that participants in both conditions got, where there were two qualitatively different ways to get to the goal. One involved not going through any notches and going around this way in red, and the other involved going through one of the notches, and that's in black here. And so what this allows us to do is, if people are only thinking, oh, and critically, the notch, the one that includes the notch, is shorter than the one that doesn't include the notch. And so if people are construing the maze in terms of blocks only, then they'll take these longer paths. But if they're construing it in terms of blocks and notches, then they'll take the shorter path that goes through a notch. And the kind of the critical thing here is this what we're calling critical notch, which is like the notch that you would go through if you were taking the shorter route. Okay, so what I'm going to show you here are the results on the test trial. So this is the proportion of people who visited the critical notch, took the shorter route in the notch unnecessary versus notch necessary trials, training trials. And after on the first test trial, where you can either go through the notch or not to get to the goal, people who went through the notch necessary training were very likely to take the shorter route, and people who were in the notch unnecessary condition were much less likely to take the notch, even though it was the shorter route. And as we go, as kind of time goes on, eventually people in the notch unnecessary condition start to pick up on going through the notch. But in this case, they don't reach the same level as notch necessary, although if these test trials are much longer, maybe they would. And so this indicates that, it's good to go through the notch. People are adapting to go through the notch to take the shorter route, and they're motivated to, they're incentivized to take the shortest route. But even so, they've kind of solved the problem. They're solving the problem in these early test trials in a blocks only way. And that is a kind of functional fixedness where you're kind of thinking about only some of the affordances of the object and ignoring other ones, even though it's all in front of you. It's all the information is technically in the stimulus in front of you. So the other thing that's interesting is that even though the sequence of actions that involves going around the blocks is longer, people actually spend less time planning on those. And this is kind of independent of the training condition. So what I'm showing you here is the first move log RTs in each of these conditions for each test trial. And so these are the participants who visited the critical notch, whereas these are the participants who did not visit the critical notch. And so people are faster when they're not visiting the critical notch, which is indicative that they're faster when they're only thinking of things in terms of blocks and not blocks and notches. And so this is kind of another challenge to this idea that we're just simulating a sequence of actions. In this case, it looks like a lot of the time is taken up by kind of searching not for actions, but for objects in the environment to reason over and do planning. So kind of from a kind of formal perspective, we can ask, okay, well, how can we account for these kinds of phenomena? And I won't go into too much detail about it, but the kind of general approach is to think of kind of this construal process as a hierarchical process, where you're still kind of forming construal on a particular trial and planning with that, but maybe that's guided by this kind of higher process of selecting a construal set, and in this case, these construal sets are the blocks only set versus the blocks and notches set. And we can think of this as a kind of hierarchical process where there is a cost to switching between different construal sets. There's a cost to switching between thinking of the mazes in terms of blocks only versus blocks and notches that is kind of connected to these kind of old ideas around switch costs in the cognitive control literature and task switching literature. So what I'm excited about with this this way of thinking about things is that it really kind of makes clear this distinction between what you might think of as like procedural automaticity, where we're kind of, which is kind of typically how like model-free learning mechanisms are thought of, where you're kind of learning a habit that is just an action, versus a more conceptual kind of automaticity, which is, we're still engaged in a very cognitively demanding process of planning, but there are certain parameters of that planning process that are rigid. Namely, you're kind of forming concepts, you're applying certain kind of ways of thinking about things in the world that's rigid. And even though you're engaged in planning, even though you're engaged in a very active process, you're still kind of subject to these weird biases in kind of that prevent you from doing the optimal thing. Cool. So I'm very excited about kind of these ideas and kind of how to think about construal, but I also think there's a kind of a larger kind of set of questions around how do we kind of think about human problem solving, kind of given more modern tools of cognitive science and kind of more modern theoretical and empirical and methodological tools. And so I think I'm very excited to kind of explore this space more. I talked about this work on value guided construal. We're also doing some work with Carlos Correa, who is a graduate student at Princeton, who we've been very interested in kind of these ideas around hierarchical planning and whether we can apply a similar kind of resource rational lens to the idea of hierarchical planning. just to kind of give you an idea of what the approach is here, we can kind of think of, again, like the representations that you form of a problem as a kind of choice in and of itself. Now, what are the things that constrain those choices? Well, in the case of hierarchical planning, the big role that hierarchical planning plays is that it makes computation easier. And so the idea here is to say, well, if we're kind of planning in the fully kind of monolithic version of the task, it might be much harder to do so than it is to kind of set a sub-goal, plan to that sub-goal, and then from that sub-goal plan to the goal. And so this, what I'm showing you here on the right, is kind of the result of applying this idea in the case of A star in a grid world, where on the top, there's no sub-goal, on the bottom, there is a sub-goal, and as you can see, it takes much less computation to get to the sub-goal and to the goal than it does to get to the goal from the start state. Again, this kind of, it gives us a useful frame for thinking about, okay, where did these representations come from? What are the kind of constraints on people's problem-solving computations that lead to these types of representations being formed? And then kind of what kind of got me interested in a lot of these things in the first place was thinking about things from a kind of social theory of mind perspective, because in many ways, theory of mind is a form of meta-reasoning. We're kind of reasoning about another person's mind and kind of making inferences about that. And then when we're trying to plan with respect to another person's mind, we have to kind of have a generative model of that mind. And I think a lot of the issues that come up in both of these cases are very closely related. So yeah, just some final closing thoughts before questions. So I kind of started out by talking about this idea of value-guided construal, and the kind of main thing that we're trying to address here is this kind of old problem that even Newell and Simon identified way back when, which is where does the problem representation come from? We have a model that, given a problem representation, can do search and come up with very smart things, but where does the problem representation come from? In humans, that has to come from somewhere. We're not machines. We don't get that for free. And the way we've approached this is to think about it as a kind of resource rational process, controlled ad hoc resource rational representations that are formed in the service of goal-directed planning. And another thing I want to emphasize is that this isn't kind of inconsistent with these other planning mechanisms like tree search and so on. It's totally consistent, and we can kind of have all of these. Clearly, people are engaged in a whole bunch of algorithmic processes to solve problems. I think on a higher level, what's kind of neat about this is that it really highlights this relationship between attention, things like structured representations of problems, and ultimately how those are all grounded out in a kind of value-guided decision-making. And finally, I think what's kind of nice about this way of setting things up, kind of from a normative perspective, is that gives us a framework for kind of investigating things at first an algorithmic level, kind of thinking about, okay, what are reasonable algorithms for construal optimization, and then kind of if we have this framework in a kind of relatively simple MDP setting, how can we extend that to multi-agent settings, partially observable settings, settings with more continuous dynamics, and so on. So I just want to end by thanking my collaborators on this work, Tom Griffiths, Jonathan Cohen, Michael Littman, David Abel, and Carlos Correa. And I want to thank all of you for your attention.
Great. Let's all unmute to give Mark a great round of applause. Thank you.
Right on time.
Yes.
That was really cool.